Hello students, welcome to TJ Akshar Academy YouTube channel. In this session, I am going to discuss work, power, energy. In this, kinetic energy. If you like this video, please subscribe to our channel. Please share your valuable comments in the comment section. Okay, let us go to the today's session. First one, energy. What is meant by energy? Let us discuss. Energy of a body is capacity of doing work. So, capacity of doing work is known as energy. Our ability to do work is known as energy. Now, let us discuss examples. A moving vehicle possesses energy since it does work against friction and air resistance before coming to rest after the engine is switched off. Here in this picture, a car is moving along the straight road. So, a moving vehicle possesses energy since it does work against friction and air resistance before coming to rest after the engine is switched off. Now, let us discuss next one. Water stored in a dam has energy since it can run the turbines when the water flows down the turbine. Next, in machines, we are interested in mechanical energy. A body possesses mechanical energy in two different forms. That is, one is kinetic energy and other is potential energy. So, energy is in different types, that is two types. Those are, one is kinetic energy and other is potential energy. Kinetic energy, nothing but the energy possessed by a body by virtue of its motion is known as kinetic energy. The energy possessed by a body by virtue of its motion is known as kinetic energy. Next, potential energy. Potential energy, nothing but the energy possessed by a body by virtue of its position or configuration is known as potential energy. In kinetic energy, motion. In potential energy, position or configuration. Next, kinetic energy. Kinetic energy is the energy possessed by a body by virtue of its motion is known as kinetic energy. It is measured by the amount of work that the body can do against an opposing force acting on it before coming to rest. Now let us discuss with example. A vehicle in motion, a satellite going around the earth, a bullet fired from a gun. Here the energy possessed by a body due to its motion. Vehicle in motion, nothing but a vehicle is in moving along the road, a satellite going around the earth. Third one, a bullet fired from a gun. Last one, water flowing along a river. Now we will discuss expression for kinetic energy. A body of mass m is moving with a velocity v. A uniform force opposes the motion to bring the body at rest in a displacement s. The uniform acceleration of the body due to force is a. Here mass m, velocity v, displacement s and its acceleration is a. From equation, the third equation of motion is v square minus u square is equals to 2as. From this equation, here v is 0 and u becomes v. So, 0 minus v square is equals to 2as. So, from this we are writing for the formula for acceleration, a is equals to minus v square by 2s. Now, the opposing force of the body, that is F is equals to ma. Now, substituting acceleration formula in this, then we get F is equals to minus mv square by 2s. By Newton's third law of motion, the force applied by the body, that is equals to minus F. So F is equals to minus of minus mv square by 2s, minus of minus plus. So F is equals to mv square by 2s. Now work done by the body against the opposing force acting on it is W is equals to F into S. So substituting F in this, W is equals to mv square by 2s into s. S gets cancels. So W is equals to half mv square. Here work done is kinetic energy. So kinetic energy is equals to half mv square. This is the expression for kinetic energy, half mv square or 1 by 2 mv square, where m is the mass, v is the velocity. Now we will discuss relation between kinetic energy and linear momentum. When a body of mass m moves with a velocity v, its linear momentum is p is equals to mv. Linear momentum is denoted by letter p, nothing but the product of mass and velocity, that is p is equals to m into v. This is equation number 1. And kinetic energy K is equals to half mv square. Consider this as equation number 2. From equation 1, V can be written as P by M. Consider this as equation number 3. Substituting equation 3 in equation 1, we get kinetic energy is equals to half m into P square by M. M here cancel is can be written as half p square by m or p square by 2m. So kinetic energy is equals to p square by 2m. This is the relation between kinetic energy and linear momentum. Kinetic energy and momentum. Kinetic energy Ke is equals to p square by 2m. And momentum p is equals to root of, taking cross multiplication, 2 root of 2m into e. From above relation, it is clear that a body cannot have kinetic energy without having momentum, and vice versa. A body cannot having momentum without kinetic energy, or a body cannot have kinetic energy without having momentum. Okay. Now I'll discuss important note. When a bullet is fired from a gun, the momentum of a bullet and gun are equal and opposite. So the kinetic energy of two bodies having the same magnitude of momenta are in the inverse ratio of their masses. So K1 by K2 is equals to M2 by M1. The kinetic energy of the bullet is greater than that of the gun. Now I'll discuss MCQs. Two balls of different masses have the same kinetic energy than the heavier ball has greater momentum, lighter ball has greater momentum, both balls have equal momentum, both balls have zero momentum. Two balls of different masses have the same kinetic energy, then heavier ball has greater momentum. First option is correct. Okay, next. Now I'll discuss work energy theorem and applications. Work energy theorem. The work done on a particle by the net force is equals to the change in kinetic energy. So this is the work energy theorem. Work done on a particle by the net force is equals to the change in kinetic energy. That is, force is equals to change in its kinetic energy. So now I'll discuss proof. A particle of mass m is moving with initial velocity u. Here in this picture, this is the particle of mass m and it is moving with initial velocity u. When some external force F is acting, its uniform acceleration is A. Here external force F is acting, its uniform acceleration is A. its velocity becomes v after displacement of s. This is the final velocity. Its velocity becomes v after displacement s. Here s is the displacement. A body is moving from A to B. Work done by the net force W is equal to Fs, or W is equal to ma into s, since F is equal to ma. Now this can be written as m into a, nothing but from the third equation of motion, v square minus u square by 2s. S cancel. So m is equal to v square minus m into v square minus u square by 2. So this can be written as half mv square minus half mu square. So work is equals to final kinetic energy minus initial kinetic energy. So W is equals to Kf minus Ki. This is the work energy theorem. Half mv square minus half mu square. When where here Kf and K are the final and initial kinetic energies. Final and initial kinetic energies. Next, Kf minus Ki is the change in kinetic energy of the particle. Hence, the theorem is proved. Now, we will discuss work energy theorem for a variable force. Consider one-dimensional motion of a body of mass m, which is acted upon by variable force if at any instant the speed of the body is v, then at that instant kinetic energy of the body k is equals to half mv square. The rate of change of kinetic energy is, that is, dk by dt is equals to d by dt of half mv square. So that is equals to dk by dt, that is equals to m of dv by dt into v. Here we are doing here derivation m into dv by dt, differentiation dv by dt into v. M into this complete change in velocity, nothing but acceleration, that is dma into dx by dt. Now dk by dt is equals to f into dx by dt. dt gets cancels, dk is equals to f into dx. So integrating on both sides, integration of ki to kf dk is equals to integration of xi to xf f into dx. So kf minus ki is equals to integration of xi to xf f into dx. This is work energy theorem. It states that work done by a force acting on a body is equals to change produced in the kinetic energy of the body. Now discuss. Note, this theorem is not applicable to a single particle but also for a system. So when it is applied to the system of two or more particles, the change in kinetic energy of system, that is equals to the work done on a system by the external as well as internal forces. So work energy theorem is also applicable to a system under the action of variable forces, conservative and non-conservative forces. Applications of work energy theorem in various situations. A particle of mass m is thrown vertically up with a speed u, neglecting the air friction. The work done by gravitational force as particle reaches maximum height is W is equals to delta k, that is equals to kf minus ki, or W is equals, this can be written as minus half mv square. So since kf is equals to 0. Next, second one, a block of mass m slides down on a frictionless smooth incline of inclination theta to the horizontal. If h is the height of incline, The velocity with which the body reaches the bottom of incline is, here this is the inclined plane and it is the h, the height of incline. Now we are taking this, a block is moving with the initial velocity, here u, final velocity v, and this inclined plane making an angle theta. We are finding the velocity with which the body reaches the bottom of incline. W is equals to delta k, that is equals to mgh, that is equals to half mv square minus 0. So v square is equals to, from this, 2gh, v is equals to root of 2gh. So this is the velocity with which the body reaches the bottom of incline. V is equals to root of 2gh. Third one, a bullet of mass m moving with velocity v stops in a wooden block after penetrating through a distance x. If f is the resistance offered by the block to the bullet, then W is equals to kf minus ki. So minus fkx is equals to 0 minus half mv square. So f is equals to fk. So fk is equals to half mv square by x. Fourth one, a bullet of mass m is fired horizontally with a velocity v, which strikes a wooden block of mass m suspended vertically. If the bullet is embedded in the block, the height h to which the system would rise is, here this is the block m and fired horizontally with a velocity v, which strikes the wooden block of mass m suspended vertically. Here this is the bullet, we have fired horizontally with velocity v. Then by the principle of conservation of linear momentum, mv is equals to m plus m into v1. So or v1 is equals to mv by m plus m, where v1 is the common velocity of bullet block system. By work energy theorem, W is equals to kf minus ki. So minus of m plus m into gh is equals to 0 minus half m plus m into v1 square. Therefore h is equals to half 2g into mv by m plus m whole square. Now I will discuss MCQs. The total work done on a particle is equals to change in its kinetic energy only if the forces acting on it are conservative, only if gravitational force alone acts on it, only if elastic force alone acts on it, for any kind of force acting on it. The total work done in a particle is equals to change in kinetic energy for any kind of force acting on it. The work done by all the forces on a system equals the change in total energy, kinetic energy, potential energy, none of these. So the work done by all forces, external and internal, on a system equals the change in kinetic energy. Now I will discuss potential energy. Potential energy, nothing but potential energy of a body is the energy possessed by a body by virtue of its position or configuration. Now I will discuss example. Stretched or compressed spring. See this figure. Here we are stretching the spring or compressed spring. Here it changes the, whenever we are stretching or compressing, its position is changing. Shape of this spring is also changes. Water stored in a overhead tank. This is the picture, water stored in a overhead tank. Next, expression for gravitational potential energy. Let us discuss. A body of mass m is on the ground. It is lifted vertically upwards through a height h. See, this is the body mass m and we are lifting upwards through a height h. The work done by the external agency against the gravitational force is W is equals to Fs. F is equals to mg, S is equals to h. W is equals to mgh. This work gets stored as potential energy of the body. So stored energy nothing but potential energy. Potential energy of the body, that is U is equals to mgh. Potential energy is denoted by letter U. So U is equals to mgh. First one. Note. Potential energy can be positive or negative. The potential energy of a spring. See here, the figure shows one end of a massless spring attached to a rigid vertical support and other end to a block of mass m, which can move on a smooth horizontal surface. See, this is the massless spring. One end is attached and other end a block of mass m. One end of massless spring attached to a rigid vertical support and other end to a block of mass m, which can move on a smooth horizontal surface. Let x is equals to 0 denote the position of the block when the spring is its natural length. In an ideal spring, the spring force Fs is directly proportional to x, where x is the displacement of the block from equilibrium position. This force law for the spring is called Hooke's law and is mathematically expressed as Fh is equals to minus kx. The constant k is called the spring constant. Its SI unit is Newton meter inverse and its measure of the stiffness of the spring. The negative sign indicated direction of Fs in always opposite to change in length. To calculate the work done on the block by the spring force as the block moves from undeformed position, that is x is equals to 0 to x is equals to x naught. So dw is equal to f into dx, that is minus kx into dx. Integration of dw is equals to integration of 0 to x naught minus kx into dx. So w is equals to minus half k x naught square. The work done by the spring force is always negative. If the block moves from x is equals to x1 to x is equal to x2, the work done by the spring force is W2 is equals to integration of x1 to x2 minus kx into dx. After integration, we are getting W is equals to minus 1 by 2 k of x1 square minus x2 square. So the work done by the spring force depends on the initial and final position of spring only. Now the net work done by the spring force is 0. Any path which done by the spring force is 0 for any path which return to initial position. Hence, spring force is conservative force. So du is equals to minus half kx square 0 to x1. That is equals to minus half k x1 square. So u minus uy is equals to minus half k x1 square. Since we take u1 as 0 when spring is at its natural length. So therefore ur is equals to 1 by 2 k x1 square. Now discuss MCQs. A body at rest can have kinetic energy, momentum, both momentum and kinetic energy, potential energy. A body at rest can have potential energy. Two springs A and B are identical but B is stiffer than A. When both are stretched by the same force, the more work is done in the case of A, B, both, nothing can be said. So more work is done in the case of A spring. Okay. Two springs A and B are stretched by applying forces of equal magnitudes at four ends. If the energy stored in A is E and that in B is E by 2, 2E, E by 4. Here the conditions two springs A and B. B nothing but K is equals to 2 KB. So the energy stored in A is E, then in B is 2E. Here they said that B spring having K is equals to 2 Ke. So first energy stored in A is E. So then in B is 2E. Okay, the second option is correct.